what gives mathematics its power and coherence is this, that it doesn't just, as I was saying in the last section, describe things in one area. It describes things in a number of areas. Let me just illustrate one simpler example, because I was talking just earlier about a differential equation. Let me talk about something which most of us will have come across. Most of us will have come across the number pi, 3.141 and so on. Pi is the ratio of the circumference of a circle to its diameter, and it will always be that. Of course, that applies in geometry, which we could just draw it on a piece of paper and you can see, you can measure it and find that the ratio is always this number. But it applies in a number of areas, because pi is actually describing the ratio of a circumference to a circle, not only for something you draw on a piece of paper, but also it describes it for engines where you've got something which is rotating, and you know that the ratio of the time that it takes to go round to the distance across, or the length that it takes to go round to the distance across, is again pi. Now, you also got other numbers that occur in mathematics which are fundamental. And one of them is not only pi, but you've got the natural logarithm E, okay, which is a base to which you raise a number, and when you've got the number or the formula e to the x, when you differentiate it, you get the same formula. So many people are interested in this, we call it a base, when you raise something to a power. And it's the something we're talking about. If you raise e to a power, right, that base is a very important base, because when you differentiate a function which involves e, you get the same function. So many people have realized that e is a very important number. E is 2.71828 and so on. So you can write these numbers down. There's yet another constant which occurs in nature, and there are plenty of these constants. And one of them is the square root of -1. Now, nobody would actually generally go to the bank and say, I want a square root of -1 number of dollars or pounds or euros out of the bank. It's totally aesthetic. In other words, it's not even something which translates to something real, and yet mathematicians use it. Now, why is this important? Because there are certain formulae, and Euler's formula is an important one here, which actually involve all three constants and are used all the time in mathematics. What the formula that I'm referring to is e to the I pi is equal to -1, right? And it's Euler's identity. So you've got e connected to pi and to I, and when you raise e to the power I times pi, you get in mathematics -1. As I said, it's Euler's identity. Now, why is this important? Because there are certain processes which are cyclic in nature. And mathematicians analyze the stability of engines and the stability of any system using quite complicated mathematics, which uses what I've just been describing, which is complex numbers. And they're using all the time these three constants. And these occur right across the mathematical spectrum of applications, not just to engines, but to all sorts of systems where you need to actually deal with different processes, where you are not necessarily actually interested in the maths itself, but you want to apply the maths to a particular situation. And there is a coherence in mathematics. It actually makes sense of reality.